Hello and welcome everyone. Thank you for joining today's webinar entitled 10 Reasons You May Not Be Measuring Power Accurately. This topic will discuss measurement, accuracy, and uncertainty, how power is measured, and other influencers. With that, today I'd like to invite our presenter. Our presenter is Yusuf Chidawala. Yusuf is the marketing manager for the Test and Measurement Division here at Yokogawa Corporation of America in Noonan, Georgia. Yusuf is a graduate of the University of Oklahoma with a BS degree in electrical engineering. He also has an MS degree in electrical engineering from George Washington University. He has over 21 years of experience in test and measurement and continues to provide expertise in the areas of data acquisition and power measurements. Again, welcome everyone. Thank you for participating. And with that, let's go ahead and get started. Yusuf, over to you.
Hey, thank you, Josh. Can everybody hear me clearly, loud and clear? Well, thank you very much. Thank you, Josh, for a kind introduction. Thank you, ladies and gentlemen, for taking the time out of your busy schedule to attend this webinar, which in my mind is a very important topic in today's fast and changing and evolving energy demanding times. Before I start, let's see, Josh, you want to give me the ball? Thank you. But before I start, for those who don't know about Yokogawa, here is a little history about our company. Yokogawa was founded in 1915, and we were the first to produce and sell electric meters in Japan. Our North American operations were established in 1957, and today our worldwide sale exceeds more than $3.7 billion. We have over 18 employees worldwide operating in 59 countries. In the U.S., our Test and Measurement Division is based out of the Noonan, Georgia facility, which is about 25 miles south of Atlanta Airport. So there's a little snippet about Yokogawa in case you didn't know. So coming to today's topic, 10 reasons why you may not be measuring power accurately. Hopefully that caught your attention a little bit, and as I think we all can appreciate and understand the importance of energy. I mean, everything we do on a day-to-day basis involves consuming energy. Right from the time we wake up till the time we fall asleep, we are consuming energy, mainly in the form of electricity. We consume energy even while we are sleeping. Either your air conditioning or your heating or your cooling is on, so you can sleep comfortably. You have multiple electronics in your house which are powered on, but still in standby mode and still consuming small amounts of energy. Most of you have mobile devices these days like phones, notepads, laptops that are charging for you so that can be used the next day. In addition, with today's revolution in the automotive industry, many of you will also have electrical vehicles that need charging for your drive and the next day. With such a huge demand, I think electrical engineers and manufacturers such as yourself are constantly looking to maximize product efficiency by optimizing power consumption and reducing all the losses in every possible way in your process design. Hence, making power measurement a very important element of this quality control, right from the design stages all the way to the production and field operation stages. So as a first step, making good and accurate power measurements and choosing the right measurement device is a vital part of this process. Something that is built for purpose, built to accurately and reliably measure power. Even if you think you're using the most accurate device, there may be several factors that affect making these measurements, and your measurement device and techniques must account for these factors that you may or may not be aware of. And that's what we hope to highlight in today's webinar. So let's start by, as a first step, this is just a brief overview of all the topics that I would like to cover today. So let's start by understanding what a measurement really is, right? So what is a measurement, right? As an example, if you are looking to measure voltage of up to 100 volts, you will most likely look for a device, say example voltmeter, that can measure up to that range. Voltmeter manufacturers will state that the measurement rating for their measurement device is 100 volts. But what does that really mean? Is that a rating? Is that an indication? Or is that a calculated guess? It's certainly not a measurement, because when you actually go to measure the voltage and the device is going to show you 99.98 or 100.02, you will notice a slight error in this expected value versus the measured value. Can we ignore this error? I don't think so, because this measurement uncertainty will eventually affect the overall design of your circuit, and eventually affect the overall behavior and efficiency of your component or your end product. Similarly, what if you were generating power and the power plant was rated for 10 gigawatts maximum power? Does that mean that the plant will generate 10 gigawatts at all time? Most likely not. It will either be a value less or more, depending on one or various factors. Um, so what is a measurement? Well, a measurement is an object that can be judged by the following meta measurement criteria. It'll have a type, which is a scale of measure. It'll have a unit, which is a standard of measurement or a physical quantity. It'll have a magnitude, which is the level or size of that measurement. And it'll also have an uncertainty related to that, which is the error in magnitude or the error in level. So these are 4 criteria that make up a measurement. Now, you may ask, what is uncertainty, right? In reality, no measurement is ever correct or exact. There's always going to be an unknown or a finite or non-zero difference between a measured value and the corresponding actual value or a true value. So this difference is what should be stated as uncertainty. Based on my previous example of 100-volt measurement, the measurement has an uncertainty of plus or minus 200 millivolts when measuring a 100-volt signal at a 100-volt range. Very commonly, instrument manufacturers will use the word accuracy to define this uncertainty. So in this case, the uncertainty of the above voltmeter can be stated as having an accuracy of plus or minus 0.02% when measuring a 100-volt signal at the 100-volt range. So the words uncertainty and accuracy are used interchangeably. One is, referenced in an actual, a unit, and the other one is referenced in percentage. So every measurement will have some type of an error, and usually comes from either the analog front end or the A to D converter or a programmable gain amplifier, or even the linearity and the frequency response of that amplifier, or all of them. The example I just gave you is a simple example of measuring voltage. Power measurements, on the other hand, also are affected by the same reasons and a few more. So to better understand this, let's first take a look at how power is measured, right? Going back to the theory, power is calculated by multiplying the instantaneous voltage times the instantaneous current, and then integrated over a period of time divided by T. All true power analyzers or power scopes measure true power in line with this theoretical formula. They make use of certain digitizing techniques to multiply instantaneous voltage times the instantaneous current, and then integrating it over a period of time and dividing it by T. But what really happens on the backside of this power measurement device, right? So let's go through that. Well, there are 3 steps, right? The first is the analog front end, where signal go through a series of normalization and sampling circuits, and then the signals are digitized using the A to D converter. Basically, the voltmeter and the ammeter front end of a power meter or an analyzer will sample the instantaneous voltages of current and voltage and current, and then digitize them, right? In the next step, it then computes the instantaneous power by multiplying the instantaneous voltage times the current, and integrating those samples within a chosen interval to compute the power and the RMS values of voltage and current. Lastly, it'll perform secondary computations like calculating apparent power, reactive power, power factor, harmonics, and all different other types of parameters that are associated with power measurement. Scaling factors are applied as appropriate to give you those measurements in real time. right? Um, so, what is important in the first two steps out here? Because the first two steps is where most of your error comes from in the form of amplitude uncertainty. This amplitude uncertainty can be caused due to internal phase shifts, burden losses, common mode rejection ratio, external sensor uncertainty, uncertainties due to your environment, temperature. Those are some of the factors that contribute on towards the amplitude uncertainty. Then there are other uncertainties that come from period detection based on how clean your signals are and if certain filters need to be used to detect this measurement period. Um, uh, Remember, in power measurement, this period detection is one of the key things in measuring your good values for RMS and power, right? So most of the uncertainties are contributed from the first two steps of this measurement process. Um, so let's take a look at the amplitude uncertainty and how you state that that comes from the first step. In general, it is expressed in terms of percentage of range and percentage of reading. The range error that, as I've shown out here, comes from the analog side of the input circuitry that normalizes your signals, which in turn is digitized by passing through the A to D converter. This portion has multiple arrangements of voltage dividers, gain circuitries that all have its own characteristics and uncertainties associated with it. So when you typically changing a measurement range on a device, it will change the path which your signal will flow through, and that will change the uncertainty. So this contributes to one part of the amplitude uncertainty. The second uncertainty is related to the actual A to D converter and the type and configuration of amplifiers used in that circuit. The linearity and the frequency response of these amplifiers will vary based on different conditions, but the uncertainty will also depend on the synchronization signals used to detect the measurement period. And this is what is known as reading error, right? So when you combine the two, you get a complete picture of what your amplitude error or uncertainty is going to be. All right. Um, so let's take an example, of how to calculate uncertainty. If you take a measurement uncertainty of a voltmeter we selected in our first example, and see what the uncertainties are if you're measuring 100 volt RMS signal at that 100 volt range. Stated that the accuracy provided by the manufacturer is 0.1% of range plus 0.1% of reading. So if you work through the math, as I've shown out here, you will notice that there is an uncertainty of plus or minus 200 millivolts as you calculate 0.1% of 100 volts plus 0.1% of range reading, and that will give you 0.1 plus 0.1, which is 0.2 volts, right? Many manufacturers will only state the reading error, and you can see that you have to account for the range error as well, which is because your actual error is slightly larger than just your reading error. So when you're looking at power measuring device, make sure that you look for these stated uncertainties, not only for voltage and current, but also for power. If you're measuring harmonics, then device should also state accuracies or inaccuracies for the harmonics as well. Since you're measuring power and that's what the device is purpose-built for, you definitely should look for the power uncertainties that are provided there. Okay. So now that we know that how power is measured, let's take a closer look at how some of these uncertainties and how they are introduced as the signal propagates along the measurement path. The first one up is basically internal phase shifts, right? As we know, to measure power, we need to measure both voltage and current instantaneously or simultaneously, and then compute instantaneous power. But looking at the diagram, the voltage and current, each of them have their own separate electrical paths. To measure current, we need accurate internal shunt on the front end. The voltage measured across that shunt is then passed to an amplifier in case a small voltage drop needs to be amplified for the A to D. On the other hand, the voltage measurement does not require a shunt, but may need an attenuator to bring that high voltage down to the A to D's measurable level. But you can see both the signals have different obstacles in the path. And you see that even though the signals are applied to the inputs at the same time, by the time it reaches the A to D, there will be a slight phase shift in voltage and current as they both arrive at the A to D. So how does this affect your power measurement? Well, ideally, if you look at the real values or waveforms of an AC power signal, right, the voltage and current are either in phase or out of phase. And if it's out of phase, depending on the nature of the load, it can be either leading or lagging. But if you look at the average power, and basically the average power is computed, and you can get an expected value of average power. Now, after going through the actual measurement circuit, this is what the waveform looks like, right? If you compare the current and voltage waveforms from the previous slide, you will see that they are slightly shifted due to that behavioral characteristics of the internal circuit. In addition, you will also notice that you have a different value for average power, so your actual measured power is different from your expected power. So this effect, somehow needs to be corrected or accounted for. A typical data acquisition measurement will not tackle this. However, a power analyzer, on the other hand, will correct for these internal behaviors and give you an accurate account of your power measurement. In fact, they will state the accuracy. So, this reading and range in this front end and this digital converter will actually will be accounted for in your reading and range errors. So, that was the one factor that contributes towards the uncertainty. Let's look at another factor, right? Common mode rejection ratio. So, apart from just internal phase shifts between voltage and current, you also have to be cognizant of another specification called CMRR, or commonly known as common mode rejection ratio. In electronics, when we are talking about CMRR, we're mainly talking about amplifiers or differential amplifiers, so to speak. The common mode rejection ratio specification will indicate how good an instrument is at reacting to any common mode influences, like as an example, EMI, electromagnetic interference, on both the high potential and the low potential inputs of the voltage and current. So as you can see from this diagram, that the high potential path and the low potential path are different, right? And hence they will constitute different characteristics and have different uncertainties related to that. Now, if you were to short the input terminals and apply a signal, you'll notice that the signals will arrive at the A to D input at different times. Ideally, the reading should be zero, meaning it will have infinite CMRR, but because of the unequal delay due to the design, a non-zero reading will appear. And I'm sure you observed this at many times, and you've done testing on your input to make sure if it's working or not working. In general, since it's the same input, the CMRR will contribute to the amplitude uncertainty rather than the phase shift uncertainty. So your measuring device should have the capability of rejecting the influences of common mode voltage. Some DAC devices have it, others don't, but for power measuring devices, it is a key factor. So be sure to evaluate this specification well before you decide on choosing an instrument. The next topic, crest factor, right? What is crest factor, and how does it really affect your measurements and measurement uncertainties? The subject of crest factor is often confusing, and the way it's specified these days by instrument manufacturers, it can sometimes be misleading. So let's kind of start with defining what crest factor is, right? Most of you may know, but by definition, crest factor of a signal is the ratio of its peak value over RMS value. So if you are looking at a pure sine waveform, say 1 amp RMS, which I've shown out here with, by a yellow waveform, its peak value would be 1.414. Therefore, the crest factor will be 1.414, or root 2. Uh, Current waveforms are purely resistive loads and will have a crest factor of 1.414, right? However, some loads, um, some loads, uh, such as switching power supplies or lamp ballast, have current waveforms that are not sinusoidal, represented here in that green waveform that I have. They draw a current for a short time, and hence their crest factors could be higher than 1.414. Uh, but note that even though you have these two different types of waveforms, the RMS values of both the waveforms will be the same, but the crest factors are different because the peak values are different. You know, so when calculating power, if these peaks or on voltage and currents are not detected or are clipped off, then that could affect your overall power measurements. So, should you be looking for measuring devices with high crest factor rating, or should you be looking for device that supports higher ranges so that you can measure these high peaks? Um, we think it's more important to have a wider effective input range so that you can measure both low signals and have the capability to measure the high peaks, right? On Yokogawa power analyzers, the specified effective input range is 1% to 130% of the selected range. And the accuracy itself is actually guaranteed within that effective input range, right? So as an example, if we select the 150 volts RMS range with a crest factor of 3, the allowable peak would be 450 volts peak. But if the instrument can measure down to 1% of range, which is 1.5 volts RMS, then based on that definition, the crest factor would calculate out to be 450 volts divided by 1.5, that's 300. So what? Does that mean that this instrument can measure a peak voltage of 45,000 volts? Most certainly not, right? So make sure you're looking out for, that's why we think it's important to basically have a wider effective input range. On our newer Yokogawa power analyzers, under certain crest factor settings, we can actually measure and display values at 300% of the selected range, thereby providing even a wider effective and measurable input range. Um, so the bottom line is, you don't want your signals to be clipped off because it will affect your overall power calculations. So, a good power meter or analyzer should have the capability to measure those peaks and provide the accurate measurements. So, what other factors could affect uncertainty of your measurements, right? Um, External sensors. Anyone out here use external sensors to measure large currents? I'm sure you have. I've known many customers who resort to that. Typical power analyzers or power meters will be able to measure currents as high as 50 amps or 55 amps. But beyond that, you're going to have to resort to using some type of an external device to bring those large currents down to an instrument's measurable level. Using external sensors is not a bad idea, but in fact, at sometimes it's a necessity. You have to be careful. That's all when choosing one, because it will add to the uncertainty of your overall power measurements. Right? There are two types of current sensors. One is open loop type. These are typically the clamp-on type probes like Hall sensing, Rogowski coils. They usually have a voltage output, which is sometimes, voltage output is susceptible to noise, but and also have a typical accuracy of 0.5% to 3%. So if you're looking for really accuracy in your measurements, then, sometimes these are not good. You need to use something more accurate. But they are easy to install, as you can see. They're easy to clamp around the wires you want to measure current off, and some certain conditions where accuracy really is not that is acceptable, then you will end up using open loop type external sensors. The other type is the closed loop type. Example, flux gate with zero flux closed loop measurement circuits. These usually have low current output on the secondary side, that can directly be connected to the current input terminals of your power measuring device. They're highly accurate, with an uncertainty of 0.05% at full scale, depending on which ones you use. but usage-wise, they are a little difficult to install and requires a little bit of pre-planning to make your connections, because you have to make sure that your wires, before you connect, your wires are passed through the donut hole, as you can see out here in an example out here. And they also require an external power supply, so they need some kind of a matching power supply, either provided by the measurement instrument or external box. So when it comes to selecting one, you really have to evaluate these and match them to your measuring device. Typical specifications you want to look at when selecting some of these external sensors is, well, the first is, of course, primary measurement range. Both the upper and lower, you want to make sure that, depending on your measurement requirements, it can measure, the low signals that you want to, and also the high signals that you want to. What is the bandwidth of the signal? Are you measuring DC signals, or are you measuring AC signals? The accuracy of those external sensors will depend on that as well. What is the secondary output type, whether it's a voltage output type or a current output type, because you will want to match that to your measurement device and see, because your measurement device will either accept a voltage input or a current input, right? True power analyzers will accept current input. So you want to match that to your measurement device and see, what input does that accept. The secondary output range, to make sure that both the minimum and the maximum output signal from your external sensor can be measured by your measurement device. This is an important one, and many engineers either miss or miscalculate this specification. Um, let's walk through an example that can explain that a little bit better. So say you're measuring a 200 amp external you're using a 200 amp external sensor that has 200 milliamp output. On the power analyzer side, you may have a wide selection of ranges you can select, but since your output is 200 milliamps, you will, most likely, based on what I'm showing, all the ranges that I've shown here, you will most likely select the 200 milliamp range, right? Now, if you're expecting to measure 500 milliamp current using that external sensor, will the power analyzer be able to accurately measure that output signal? In this case, let's take a look. In this case, if you use 200 milliamp range, the lowest the power analyzer can accurately measure is 2 milliamps, which is 1% of that selected range. But the sensor is going to output 500 microamps. So you see, this will result in an inaccurate measurement, right? Or even a failure. You may not be able to measure it at all. But now if you're expecting to measure 2 amps using that external sensor, the sensor will output 2 milliamps, which is within the guaranteed measurement range, and this scenario will result in success. Basically, it will be a guaranteed accuracy that you're measuring 2 amps, right? I mean, our application engineers get many calls that are related to this mismatching. So, be careful, be prudent, when selecting external sensors. Make sure they're properly matched with your measurement device. Lastly, you also want to account for the stated uncertainty of that external sensor, right? If the accuracy is stated as 0.05% of full scale, then this accuracy needs to be added to the overall power accuracy. As an example, a quick and dirty way of doing this is basically square root of the sum of squares, right? So in this, by this example, if the power accuracy was stated as 0.01% of reading plus 0.01% of range, then you want to just basically take the square root of sum of squares. So you have 0.01 square plus 0.02 square plus 0.05 square, which is of the external sensor, and take the root of that. So you will see that your uncertainty is 0.055. So you see how much uncertainty an external sensor can add, because if you were to just calculate 0.01% square or 0.02 square and take the root of that, you would get approximately 0.028 or something like that, right? So adding an external sensor does does increase your uncertainty. So, okay, I think I hopefully explained that subject pretty clear. What are other factors that could affect, your uncertainties? Apart from just operating temperature range, IEC standards require that you state the temperature conditions under which accuracy is met. Usually that value is 23 degrees plus or minus 5 degrees Celsius. This is important because if the temperature of your measurement environment changes, then that could actually affect the overall accuracy of your measurement. Most manufacturers who comply with these standards will provide that specification, which is called the temperature coefficient, as I've shown out here. This is usually an additive addition to the accuracy of the operation under normal circumstances or temperature range, basically. So make sure you look for these specifications and account for them as you calculate your overall uncertainty. So now, we have discussed many of the factors that can affect the uncertainty on the front end side. The A to Ds, the gain circuits, all that stuff. So let's talk a little bit about the factor that could affect your measurement on the computation side of things, right? So let's focus on the sync source, the frequency filter setting, and the period detection, right? When it comes to accurate power measurements, the biggest one is the ability of the device to detect the period of the measurement, right? As RMS and power values for voltage and current are obtained in periods, detecting the period in power measurement is extremely important. Let's take a look out here as an example of a clean waveform, a current waveform that I have here. Now, if you use the measurement periods denoted by the yellow and the red portion of the waveform, you can see that the RMS values that are calculated will either be lower or above the expected solid blue line, right? If you use the measurement period shown in the green region, then the RMS value is same as what is expected, right? So you can see that if you don't use the correct measurement period, the measurement will not be correct. For accurate power measurements, not detecting that correct period of calculation will result in a significant error. So how does a power meter or a power analyzer, measure this period? Well, it doesn't. Okay, it actually measures based on measurement intervals. On Yokogawa power analyzers, this measurement interval setting is provided via the update rate setting, which can either be set to 50 milliseconds, 100 milliseconds, 250 milliseconds, and so on. The instrument determines the measurement interval within this update rate by determining the correct period of the incoming signal. Once the period is detected, the integer number of cycles are detected within that data update period, and those cycles are used to actually calculate the RMS values of power, voltage, and current. All right. So I hope that's clear. When it comes to power measurements, it's important to detect the period. Now, how does the instrument detect the correct period of that incoming signal? Well, you do that by either using a good synchronization signal and maybe some filters if needed. For sine waves, it's easy to detect the zero crossing, but for distorted waveforms like current signals of commercial power, it's a little difficult. However, the voltage signal is a lot cleaner, and that can be used as a good sync source. Similarly, if you're measuring PWM signals where both voltage and current could be distorted, voltage more than current, in these cases you would need some type of a filter, a frequency filter, to achieve a cleaner signal, and then you can use that signal to determine the correct period reliably every time, right? As an example, I've shown you a circuitry out there which is for one of our power analyzers. You can see the frequency filter that is used to detect the zero crossing, right? So make sure this is the key. Just my message here is this is the key to actually detecting, making good and accurate power measurements. The next factor, one of the most important ways to maintain your confidence in your measurements is to perform regular calibration of your device. Most manufacturers will provide an accuracy validity anywhere from 6 to 12 months. It'll basically have a recommendation that you calibrate this every 6 months or 12 months. But to get good confidence, you got to calibrate your devices regularly. And the two most common standards for traceability used here in the United States are NIST and ISO 17025. These are both standards that are related. There are other standards also that are related to defense and aerospace industries, but even for those industries, sometimes the ISO 17025 is very commonly accepted. Yokogawa provides calibration and traceability to both these standards. In fact, our calibration lab is certified to the A2LA standards, and it is out here in the Newnan, Georgia office, located in the Newnan, Georgia office. So all our instruments are can be calibrated and guaranteed that way. You know. So I guess I've kind of gone through a lot of the the factors or the reasons that are covered that are directly affecting the overall accuracy of your power measurements. So now allow me to highlight some other considerations that you may also have to decide on when choosing your power measurement. Um, you know Apart from today, apart from electrical engineers, there are other engineers from other disciplines that are also tasked with making power measurements, and they often struggle with choosing the right device to make those power measurements. The most common choice struggle that you will make is, should I use a data acquisition device to measure my power, or an oscilloscope, or should I use a power analyzer, right? um, both of them have their pros and cons. A typical DAC device will only specify DC accuracy specifications. They may or may not specify any AC specifications. They're also usually voltage inputs and need external sensors for current input, right? Even in the low current ranges, whereas a power analyzer would directly accept those current signals. The accuracies don't include probes, so you have to calculate those accuracies out, include those accuracies separately with the overall calculation, and they may not address any of the uncertainty factors that I described today in this presentation. On the other hand, power analyzers are purpose built. They're built to measure power accurately and will hence have both DC and AC accuracy, for voltage, current, and power. Accuracies are guaranteed for benchmarking electronic devices. In addition to the voltage, current, and good power accuracies, power analysis will also state the harmonic measurements. I didn't go into this subject more, but this is another thing a power analyzers do better than traditional DAC devices, because you have the stated traceability to those harmonics accuracies. Lastly, some other pros and cons of when comparing a DAC versus a traditional power analyzer. There are you have high channel count. The DACs can actually support high channel count. They can provide mixed signals. So if you have different types of signals that you're measuring apart from just voltage and current on a phase, you can measure temperature. It supports the complex triggering for capturing and analysis phenomena, and actually can rely on understanding the complex systems. Whereas a power analyzer is designed for one purpose, and measuring power and related parameters very accurately. They are well suited for benchmarking component efficiencies, your designs, and even they're very good for in manufacturing areas as well. And it produces repeatable and consistent results. I mean, so in general, there is no wrong solution. It's just a matter of comparing both the capabilities and really what your application requires you to use. Um, So in conclusion, I would like to add that Yokogawa has both types of solution: DAC-based solutions that can do power analysis, and also traditional averaging style power analyzers. So depending on your application, we have solutions that can address or fit your measurement needs. Would also like to add that all products offered by the Test and Measurement Yokogawa are serviced, calibrated, and supported from the Newnan, Georgia facility. We have product, application, and software support that is provided through a network of field sales engineers and also application engineers here in the Newnan office. So in short, we're here to consult you to making successful power measurements and making you choose the right instrument for your application. Um, if you are, one last slide I have, if you are an existing Yokogawa user, or even if you're not, and use another product for your power measurements, please contact us and see how you can make use of this limited time trade-in, trade-up offer. I think it's a pretty good discount of 20% on a working unit. So do let us know if you have such an opportunity. Um, so here is a recap slide for some of the topics we covered today. I hope you found this webinar useful and leave a little wiser towards making your choices and decisions. With that, I would like to thank you all for taking the time to attend this webinar. Um, I'm not sure how much time we have left, Geoff, but I'm open to any questions that may have come through.
Great. Yes. Thanks, Yusuf. Very informative. A lot of good information. Again, we'll make sure to get everybody a copy of the recording and a copy of the slides in the next few days. Those of you that would like to submit questions can now do so by using that Q&A icon, and we'll get to them as quickly as possible. Here's our first question that we've got, Yusuf. It says, would there be a difference in uncertainty between a single-phase power measurement and a three-phase power measurement?
Yeah, actually, yeah, there will be. When you're measuring a three-phase system, you're going to have three different voltages and three different currents, right? So there will be a slight uncertainty difference. In fact, actually, on our power analyzers, we actually have an uncertainty calculator that calculates uncertainty on a single phase, a three-phase three-wire system, and a three-phase four-wire system. On a three-phase three-wire system, basically, if you look at the calculation, you're going to use the 2 watt meter method to calculate power. So you have to account for those 2 watt meter, the uncertainties of both the watt meters, and typically the multiplier is root 3, is actually root 3. So but yeah, I mean, we do have, it is going to be different, and you need to make sure that you calculate your uncertainty appropriately.
Okay, here's another one. It says, when you use a filter, aren't you actually filtering the signals, which will affect your measurements?
I'm guessing that question is referring to my discussion about that frequency filter. So no, actually, I think I showed that in one of the slides. You have two different types of filter. You have a frequency filter and you have a line filter. The frequency filter is solely used to determine the period of the incoming signal. The line filter is what is used to actually filter the signals. We don't use that. But in this purposes, if you have the line filters turned off and you have the frequency filter on, you're not going to be filtering your signal. You're actually just going to be using that frequency filter to detect the correct measurement period. So no, yeah, I hope that explains that.
Okay, yeah, great. Here's another question. It says, how long is the trade-in, trade-up program valid for?
As far as I know, it's valid till March of 2020. So that's what I have, the latest information. Yeah. So if you are definitely interested, please let us know. Please fill out the contact us form, and we'll be glad to get in touch with you.
Great. There was a question, somebody was asking if we have some additional webinars on power electronics, PWM, IGBT, and just power measurements. We do have a number of other webinars, and you can find them actually on our website. There's a library section, and there's a whole bunch of webinars there. And we'll also take some of your suggestions that you have for future webinars we're planning on having. Another question that came through says, to what power frequency range do you calibrate to?
To what power frequency range do you calibrate to? Well, I mean, our calibration goes through, the instrument will have its rated specifications, right? Uncertainty specifications. So a typical instrument will have its own limits, upper and lower limits, right? It will have different ranges of current, will have different ranges of voltage, will have different frequencies that it can operate on. The service manual or the calibration manual of that instrument should state, at what are the different points you need to calibrate to. So hopefully that answers the question.
Okay, great. Here's another one. It says for DC to DC converter efficiency measurements, do you recommend using EMI filters at input/output during measurement? Does accuracy reduce if EMI filters are not used because of common mode noise?
It will depend on the instrument's ability to reject that common mode, plus it'll depend on the noise on that signal. So, you know, to use those filters is definitely a choice that you're going to have to make. If you need to use it, then you're going to have to use it.
Okay. Here's another one. It says, what are the ramifications of setting the CF to 6A?
Oh, that's a good one. That's that's probably a question based on one of our power analyzers. Actually, that's a setting that's available to provide a wider and effective input range, and that if you look through the specifications carefully, you will notice that there is a certain uncertainty additive that you have to take into account when you select that 6A crest factor. So yeah, it will affect your uncertainty because you're increasing your effective input range. So on Yokogawa Power Analyzer, we actually spec that how much of that uncertainty needs to be added to the original uncertainty.
Great, thank you. Here's another question for you. It says, do you have any more info on your uncertainty calculator?
Actually, the uncertainty calculator is provided on our website. So I'm trying to understand any more info. In fact, the calculator shows all the. I mean, once you download that Excel sheet, you pretty much have, access to everything that calculator does. I'm trying to understand what more info do you need. I mean, the certainties built into that calculator were based on our published specifications. So. I'm trying to understand what more info would you need.
Maybe what we can do is we'll make sure to include that in the follow-up videos, a link directly to it, and then you guys can use that calculator. You'll have a direct link, and if you have questions, we'll always be happy to jump in and walk you through it or try to help you find what you're looking for.
Yeah, no, I would be more than happy to reach out to that person who asked that question about the uncertainty. You can have a phone conversation for sure.
Okay, cool. And here he had a follow-up question on that. He says, do any of the Yokogawa meters calculate measurement uncertainty internally?
Any of the Yokogawa instruments calculate measurement uncertainty internally?
Mm-hmm. Like within the device itself, I think is what they're asking.
No, I don't think so.
Okay, cool. And then here's another one. It says, what's your most popular PA for accurately measuring a computer server's power? Parentheses 50 watts to 750 watts, and why?
The most common one that's used is the WT300 series. In fact, SPEC, which is the Standard Performance Evaluation Council, also uses that same power analyzer to do the testing for servers. A lot of our power analyzers are certified by them to use for efficiency measurements.
Okay, cool. That's the end of the questions for today. If we didn't get to your questions, we will follow up with you via email or via phone call. We appreciate all the input today. Yusuf, you had a great presentation. We really appreciate the time and effort that was put into it. And to all of you that have joined us, thank you for taking some time out of your busy days. And we hope to see you again next time at our next webinar.
Well, thank you, Josh. Thank you, everyone, ladies and gentlemen. Thank you.
All right, we'll see you next time.